Welcome to this advanced engineering training on makeup water supply for high-density liquid-cooled data centers. Our design basis is a coastal campus, representative of a bottom or Nongsa Island environment, scaled to support 144 megawatts of IT load. Building at this scale in a marine environment creates an immediate freshwater constraint. The site provides isolated power generation and strategic regional connectivity, but lacks the municipal reserves required to support traditional or hybrid cooling at scale. To operate independently, the campus must secure its own water supply by engineering a dedicated seawater reverse osmosis or SWRO plant on site. Integrating desalination into the thermal path requires adhering to a fixed thermodynamic reality. Direct-to-chip liquid cooling does not eliminate heat, it concentrates thermal energy into a high-density liquid loop. Every megawatt generated by the servers remains trapped within the building's hydronic systems until it is physically rejected to the atmosphere. To maintain uptime, the facility's heat rejection and water supply cannot be managed as separate utilities. Instead, they must be engineered as a single continuous chain running from the processor silicon out to the sea. This system map details the requirements for moving that heat. The campus must maintain 3 independent, rigorously separated fluid domains. Maintaining absolute isolation between these loops is a non-negotiable design requirement. Domain 1 is the Technology Cooling System, or TCS, secondary loop. This circulates through the data hall. It is an ultra-pure, chemically inhibited, and degassed coolant, engineered to meet server OEM specifications. Domain 2 is the primary facility water loop. This heavy-duty industrial piping network provides bulk thermal transport, carrying the thermal load away from the IT equipment and out to the heat rejection plant. Domain 3 is the SWRO makeup loop. The desalination plant produces a treated product stream engineered exclusively to replace cooling tower evaporation. SWRO product water must never enter the IT secondary loop. These 3 domains operate under entirely different purity, filtration, and chemical specifications. Pumping raw desalination product directly into server cold plates causes rapid scaling, corrosion, and catastrophic hardware failure. Cooling a 144 megawatt deployment relies on transferring concentrated energy across these 3 barriers without any fluid ever crossing the line. We begin tracking the heat at the silicon. For this 144 megawatt deployment, 80% of the IT load, or 115.2 megawatts, is captured directly at the chip via liquid cooling. A direct-to-chip cold plate is mounted to the high-power package. Heat moves from the silicon into the liquid flowing through microchannels. The heat transfer formula dictates that dividing the 115.2 megawatt load by a 10 Kelvin difference circulates exactly 9,907 cubic meters of fluid every hour. Once the TCS fluid absorbs the heat, it arrives at a coolant distribution unit, or CDU. The CDU acts as the thermal bridge between the clean IT racks and the industrial facility systems. Inside, a plate heat exchanger allows thermal energy to pass while maintaining an impenetrable physical barrier between the TCS and facility water domains. The primary facility water loop absorbs that load. Factoring in a standard 3% allowance for pump and heat exchanger inefficiencies, this network carries 118.7 megawatts of thermal energy away from the data halls. Liquid cooling has concentrated the load for the next stage of the chain. Now that heat must be physically evacuated to the atmosphere. Beyond the liquid captured load, we must account for the remaining 20% of IT heat. This 28.8 megawatt load escapes into the data hall as ambient heat from memory, storage, and networking equipment. Computer room air handlers pull this ambient heat across cooling coils, trapping the energy inside a separate chilled water loop that feeds the mechanical chiller plant. The mechanical compressors required to run those chillers inherently add 4.1 megawatts of new thermal energy to the system. This flowchart tracks where the 2 thermal paths converge. Adding the 118.7 megawatt facility load to the 32.9 megawatt chiller load establishes the final thermodynamic boundary, a total heat rejection requirement of 151.6 megawatts. Regardless of internal efficiency, the exterior cooling towers must be sized to reject exactly 151.6 megawatts to the sky. The baseline method for rejection is the open-circuit wet cooling tower. Here, hot facility water flows over fill media, exposed directly to the outside air. The latent heat of vaporization dictates exactly how much water must evaporate to shed the 151.6 megawatt load. This process requires evaporating 223.7 cubic meters of water per hour. Factoring in blowdown, the open wet tower requires 6,446 cubic meters of makeup water daily. We can now compare this to a common industry assumption, that transitioning to a closed-circuit wet tower inherently reduces site water consumption. In a closed-circuit tower, the facility water stays protected inside a coil, while a separate spray loop wets the outside of that coil. However, the latent heat of vaporization remains a fixed physical property. To reject 151.6 megawatts, the system still dictates evaporating the exact same mass of water. The data shows that a closed wet tower demands 6,444 cubic meters daily. This is a 0.03% difference from the open tower, caused strictly by better drift eliminators, rather than a reduction in evaporation. While closed wet towers protect the facility loop from contamination, they do not materially reduce water consumption at an equal heat load. True water savings require a hybrid closed adiabatic system. These units use dry coils to reject heat without water when weather permits. As this chart shows, if the climate allows an optimized 45% wet fraction, the daily makeup demand drops to 2,900 cubic meters. Sustainable coastal cooling is achieved by utilizing dry mode hours to reduce the total wet operating fraction. The makeup water demand establishes the scale of the SWRO plant. Raw seawater is pulled through marine intakes, pre-treated, and forced through high-pressure membranes. The reverse osmosis recovery rate is 42%. For every 100 cubic meters of seawater processed, 42 cubic meters become product water, while 58 cubic meters are rejected as brine. We apply a 10% design margin to the tower's peak demand. For the all-wet closed baseline of 6,444 cubic meters, the SWRO plant must be sized to produce 7,089 cubic meters of net product. This sizing matrix shows the impact of cooling selection on the desalination infrastructure. Servicing the all-wet baseline requires 6 installed RO trains to meet the daily volume while maintaining an N+1 margin. If the facility operates on a conservative hybrid architecture, the net product requirement drops, allowing the plant to shrink to 5 installed trains. While the 144 megawatt IT load defines the magnitude of the thermal rejection, it is the cooling tower strategy that determines the variable scale and final train count of the SWRO plant. Reject streams from the process, including high salinity brine and treated blowdown, require strict neutralization and tidal modeling to ensure they do not recirculate into the marine intake. Final performance is measured by water usage effectiveness, or WUE. Both open and closed wet towers operate at a baseline of approximately 1.87 cubic meters per megawatt hour. By slashing wet operating hours, an optimized hybrid system drives that metric down to 0.84. This reduction is achieved by maximizing dry mode operation. To meet Tier 3 or Rated 3 standards, every critical step, from the marine intake to the CDU secondary pumps, requires N+1 redundancy. One train or component must be isolatable for maintenance without interrupting the IT payload. Sustainability and reliability are validated together by confirming the reduction of wet hours through weather bin analysis, while maintaining the ability to isolate any part of the hardware chain. Managing this multi-domain infrastructure requires integrated control logic. This dashboard displays the monitoring baseline, real-time WEU, basin conductivity, and SWRO train status. The loops are highly dependent. A drop in the storage tank automatically fires a standby SWRO train, while high conductivity in the tower basin triggers blowdown valves to maintain chemical balance. Accurate WEU reporting is only possible if the system can explicitly measure and control every drop of water across this logic chain. In summary, closed wet towers provide a cleanliness strategy for the facility loop. Hybrid adiabatic towers provide the water-saving strategy. By engineering the thermodynamics outward from the chip and the hydrology inward from the sea as one integrated system, a coastal campus achieves reliable cooling and certifiable sustainability.